So now we're on to the Chapter 2, Part 2 slides. In this video, I'm going to talk about atomic symbol notation. We'll introduce the concept of isotopes, and we'll look at the periodic table in a little bit more detail. So what we're looking at here is something called atomic symbol notation. And it's not necessarily what appears on the periodic table, but it's a specific descriptor for one individual atom. And it's going to tell us pretty much everything we need to know about the atom in terms of proton, neutron, and electron count. So we know a bit more about the structure of the atom now, but now we're going to talk about how this notation will describe the atom in more detail. So typically what we have is an element symbol, whatever it may be, and then as a subscript we have the atomic number, so that's the value that you see here, and that represents the number of protons, and typically it also represents the number of electrons. If the atom is neutral, then that's what we would expect. The other value that we see is in the upper left corner here, and that's the mass number, the number of protons plus neutrons. So in this particular case, with the 612 carbon, it's kind of telling us everything we need to know about that atom. So let me just write it here. So this is 6 protons, then 12 minus 6, so 6 neutrons. And there's no indication of charge, so that should tell us that the electron and proton count are the same, so 6 electrons. And what we'll see is if there is a charge, it'll be indicated in the upper right corner, and we'll get to that in a little bit. There are a lot of atoms where the proton and neutron count are going to be the same, but there's no reason for that to necessarily be true. It could vary depending on the atom. And that gets us to the concept of isotopes. And isotopes are atoms of the same element with different masses. And the way they have different masses is by having a different number of neutrons. So what makes carbon is the fact that its atomic number is 6. Atomic number means the number of protons, but it's also what makes carbon. That's the defining quality that it has. But what you can see now is that the upper left number, the mass number, is different for all of these. So now we would have 6 protons, 5 neutrons for this one. Then for this isotope, 6 protons, 6 neutrons. That's the one we were looking at before. I think you get the idea. Then 6 protons, 13 minus 6, so 7 neutrons. And then 6 protons, 14 minus 6, 8 neutrons. And again, these are all neutral, so they're all going to have 6 electrons as well. And we know that because there's no indicator of charge. We're going to see the indicator of charge in I think in the next slide. So cations are positively charged ions, anions are negatively charged ions. And one of the ways that I was taught to remember it is a negative ion for anion, but those are the ones that we're looking at. So here on this slide, we've got neutral oxygen atom, and then we've got the anion of oxygen, and we've got neutral magnesium and the cation of magnesium. So let's start with the neutral oxygen. So this is 8 protons, that's the atomic number. then 16 minus 8 neutrons. And again, this is the neutral atom, so it's also 8 electrons. So then here we have the oxygen anion, and it is still 8 protons and 8 neutrons, but now it's -2 charged, right? So that means that there are 2 more electrons than protons. Well, we already know that there are 8 protons, so that means there have to be 10 electrons. So if there is a charge, it'll be indicated in the upper right corner, and it'll be written in this way, 2 minus or 2 plus, whatever it may be. Okay, so then let's do the same thing down below. So neutral magnesium, 12 protons, 12 neutrons, 12 electrons, again, because there's no indicator of it. And then now we have the magnesium cation for the positive ion, and we can go through the same process here to see how we would assign the proton, neutron, electron count. So it's 12 protons, 12 neutrons, just like before, but now it's +2, so that means there are 2 fewer electrons than protons. So now it's going to be 10 electrons. So that's how atomic symbol notation works. So hopefully that's making pretty reasonable sense. I think once you do a few of these, then you get confident about what the information is. Just always remember that upper left number is protons plus neutrons. It's not the number of neutrons. That's kind of the thing that most commonly gets confused. So what we're talking about here is atomic mass. And technically, we're kind of reporting things in terms of atomic mass units. If you remember from the last set of slides, essentially a proton weighs 1 atomic mass unit, a neutron also weighs 1 atomic mass unit, and an electron weighs much, much less than that. So that's why that mass number is not included in the value for the total mass. You also might remember from early on in the last set of slides, we saw that Thomson, among his work in, well, I guess in addition to his work with cathode ray tubes, he also created an instrument called the mass spectrometer. And essentially, it's just an instrument that can very accurately determine the mass of a small particle. So it should make sense that that's something he was working on as he was trying to figure out the behavior of subatomic particles. You don't have to worry too much about what's going on here. Really, the only reason I bring it up is to tell you that we have an instrument that allows us to measure masses of very small things to a really high level of accuracy. And just to give you a quick idea of what happens here, essentially you add a sample to this spectrometer, it gets vaporized, and then it travels through a beam of positively charged ions that it gets bombarded by, and the behavior of this particle as it goes through this curved trajectory, the way it behaves in there in terms of how fast it moves, etc., will allow us to very accurately determine the mass of that particle. So that's how we can determine the mass to such high levels of accuracy. I think in chapter 3 we'll come back to this idea and talk about how isotopes play a role in determining the average mass of an element, but we'll get to that a little bit later. So what's going to happen, and so this kind of alludes to what I was talking about, what's going to happen in, I think, chapter 3 and 4 is where we're going to start to see it, is when we have a large amount of substance, so not just one atom or one molecule, then we need to consider the existence of isotopes, and for that reason, you're going to see that we're going to use average masses. And the way we get the average masses is we calculate it from the distribution of isotopes for a particular element and the amounts that they have. So something like carbon, more or less, it's 99% carbon, 99% carbon 12 and 1% carbon 13. So what we end up with for the carbon average mass is more or less 12.01 AMU, because that's kind of the weighted average of the two isotopes. So we're really rounding proton and neutron masses to 1 for all of this, but that's the way that we would figure it out. So not that critical until we get to chapter 3 and start doing more calculations with the periodic table. But as we're introducing the concept of isotopes, it's good to bring it up here. But we'll revisit it in more detail when we're more interested in numerical calculations coming from the periodic table. Okay, so I think the first unnumbered handout that's posted on the Blackboard page is a periodic table, a little more complicated than this because it has some mass values as well, but this is kind of the simplest picture to start with our periodic table. And so something that I probably won't talk too much about really because we don't involve ourselves with these elements too much, is you might notice this arrow here, right? And essentially that arrow is saying that set of 2 rows of elements, it fits into that gap between 56 and 71, between 88 and 103. So if we really drew the periodic table as it should appear with this type of organization, it would be really wide and short. So it wouldn't really print very conveniently or be easy to look at on one sheet of paper. So for that reason, those elements go down there. Honestly, we really aren't going to talk about the properties of elements beyond element 56, so we won't get too into any of that, but that's the reality of how it looks. Is it's a very wide table if we include those elements where they theoretically belong. So we'll talk a little bit more about that later, but as I said, for the most part, we're going to not even involve ourselves with elements really beyond 56 for most of our applications. So when we want to describe the periodic table, we can kind of simply say it's a systematic catalog of the elements, and they're arranged, the elements are arranged in order of atomic number, so in terms of proton count. And remember what I said earlier is what makes an element that particular element is simply the number of protons, so it's fairly logical to organize things by atomic number. So mostly what I'm interested in doing in this section is just kind of giving you a general idea of the layout of the periodic table. We're going to give names to some of the groups of compounds, some of the columns, just so it'll be easier to refer to them going forward. But we'll come back again in a later chapter and talk in substantially more detail about the periodic table. So for now, just kind of a brief introduction. So one of the concepts that we'll see as we get deeper into studying the periodic table will be the concept of periodicity. And periodicity really says that as we go across rows on the periodic table, we're going to kind of see the repeating of patterns. And what that really ends up telling us is that elements that are in the same column, which we call a group on the periodic table, they typically have similar properties. So as we go across any row, we'll start to see this repeating of properties. But what we're really observing is that elements in the same column, which we call group, they're going to have similar properties. Okay, so with that, we have some vocabulary. So rows on the table are called periods. columns on the table are called groups. Typically, I'll keep saying row or column along with the official terminology just to make sure I'm being pretty clear. And then, like I was just saying, something we're going to observe is that elements in the same group, the same column, are going to have similar properties. So to start with, there's kind of some simple divisions that we can make in the periodic table. And the first one is to identify the non-metals. So what you can kind of see here is this, let's say, upper right area of the periodic table contains the non-metals. So mostly those are liquids and gases. There are some exceptions to that. And then hydrogen ends up way over here because of its electron count in terms of its location on the far left. But really it belongs with the non-metals, right? Hydrogen at normal atmospheric conditions is a gas, H2. So it's more similar to the stuff we see in that upper right corner. So with that in mind, that means most things are either metals or metalloids. So one marker you may want to make on your periodic table is to follow this kind of staircase that you see here, because it delineates what we call the metalloids. So these are elements that have some metal-like properties and some non-metal properties. If you look at some of these elements, so silicon, germanium especially, these are elements that are used heavily in the semiconductor industry because they don't have the full conducting capacities of metals, but they have more controllable conductance, which gives them properties that we're definitely interested in for technological applications. So what that then means is pretty much everybody else is a metal, right? So the majority of the periodic table, kind of the left 2/3 or 3/4 of it, these are all things that we would classify as metals based on their properties that include conductivity. So most things that we consider here are metals. Okay, so then the next thing I'm going to do, and I guess the last thing I'm going to do in this video, is I'm going to label, I think, 5 columns on the periodic table just to make it easier for us to refer to them going forward. So we're going to start with some columns on the far left, and then we'll move to the far right. So we'll start with those 5 columns. I think those are the only ones that I really use the group name for, so just convenient to get these names in place so we can refer to them by these names rather than try to list the elements each time. Okay, so to start out with, this far left column, which has lithium, sodium, potassium, etc., these are all called the alkali metals. And I guess I should say, if chemistry is kind of unfamiliar to you, you're always going to have a periodic table available to you to look at. So you don't need to memorize any of the information that's on the periodic table, but knowing these group names, that's something important just because I'm going to refer to them by these names. So you should learn these names. Okay, so the far left column, those are the alkali metals. And then if we scoot over one column, so beryllium, magnesium, calcium, strontium, etc., these aren't the alkali metals, these are called the alkaline earth metals. So the alkali metals, those all have pretty similar properties. The alkaline earth metals, those all have fairly similar properties. And in general, I would say there are a fair number of similarities between the behavior of the alkali metals and the behavior of the alkaline earth metals. Okay, so now let's shift to the right side. So we're going to look at the 3 rightmost columns here. And so now we're looking at the column with fluorine, chlorine, bromine, iodine, the farthest, second farthest to the right. And these guys are called the halogens. So you may be thinking about like halogen lamp. And that's because a lot of times those are elements that are part of the lamp as gases often, and so that's what the halogens are. Okay, I think I'll go all the way to the right, and then we'll introduce one more, and then that'll be it for now. Oh, I guess while we're here, let me pick one of these to just kind of transcribe. So I know it's hard to read, and I don't want you to read these numbers. When it's time to worry about numbers, I'll give you a easier periodic table to read. So what I said earlier is that the atomic symbol notation doesn't necessarily relate to the way information is laid out on the periodic table. You can kind of do it however you want. So in this case, this is up top the atomic number. So that's the number of protons. And then down here, this is the average atomic mass. So let me do the same thing for carbon, since that was the example we were using earlier. So the way carbon is written on here is 6, the atomic number, and then 12.011, that's the average atomic mass based on the weighted average from the naturally occurring isotopes. So this particular periodic table, that's how it's laid out. I think the other ones I'm going to give you are pretty similar. Like I said, when you do need those numbers rather than just a general layout, I have a cleaner one to look at. I think the one I posted as your first handout, that's a lot easier to look at as well. Okay, one more family of elements to look at, and that'll be it for this video. Oh, two more, I guess. Farthest to the right, these are all gases at room temperature, and they're called the noble gases because they're relatively unreactive. In fact, the only one of these we really know to form molecules is xenon. The rest of them really aren't interested in forming molecules with other atoms. That's why we call them the noble gases. They're kind of above interacting with the other elements. So what we know about the noble gases is that they're uniquely stable because of their electron configuration by being at the end of a row. And something we're going to find out is the other elements are going to gain and lose electrons in order to get an electronic configuration identical to one of the noble gases because that's uniquely stable. So this is helium, neon, argon, krypton, xenon, radon. And then the last group name that we're going to talk about, and I use this once in a while, but I think it shows up in the text a bit more often, is chalcogen. And the chalcogens are the column to the left of the halogens. So this is oxygen, sulfur, selenium, etc. I think that's tellurium, yeah, and polonium. Okay, so those are the column names that I want you to be aware of. I think in the homework I ask a few questions about the column names or which one does this one belong to. So you should learn those names just because it'll be easier to follow along with lectures, and it's something that I would like you to learn. Okay, I think that's a good start here for the periodic table. In the next video, we'll start to talk about how molecules form a little bit. Particularly, we'll talk about ionic compounds once we get to that point. But for now, I just wanted to get the atomic symbol notation clear, talk about isotopes, and then give you a brief introduction to the periodic table.